Hello. Now let us go to the second part of the stability of nonlinear systems. So in the last lecture, we had seen the notion of stability in the sense of Lyapunov. Okay. So in this session, we will see the approaches, some approaches for analyzing the stability of nonlinear systems. Okay. In the last lecture, we had defined three terms. We had defined three terms in the sense of Lyapunov. One is called the Lyapunov stability, and where in the case of Lyapunov stability, we had discussed about the stability of the equilibrium point xe. If I have an equilibrium point xe, that means the solutions, if I have some solutions starting very near to the equilibrium point, and or in fact very close in the neighborhood of the equilibrium point, and it does not go very far away, and it remains very near to the equilibrium point, then we can say that the system is Lyapunov stable. And then we had also seen a bit more stronger notion for stability, which is called as asymptotic stability, where the I will write it down, asymptotic stability, where we saw that if we start from an initial condition and the solutions converge to the equilibrium point as t tends to infinity, we can say that the system is asymptotically stable. And a bit more another notion for stability, which gives the convergence rate of gives information about the convergence rate of the system, is called the exponential stability, where we get a bit more stronger notion for stability. That means it converges at a faster rate. That means if the solutions converge at a faster rate, then we can say that the system is exponentially stable. Okay. All these stability definitions were defined in the sense of Lyapunov. Okay. In fact, Lyapunov had also defined certain approaches for analyzing the stability of the system. That is what we are going to see in the coming lectures. And two different methods that he had devised was, one was a direct method, and the other one is the indirect method. Okay, these are the indirect method. These are the two approaches which through which we can analyze, we can check whether the system is stable or not. So in today's lecture, we are going to see the indirect method. Okay. So there are two methods for analyzing the stability of Lyapunov methods, which was devised by Lyapunov. And one is a very powerful method, which is called the Lyapunov direct method. The other one is an indirect method. It is called the first method or reduced method, where if you are given a system equation x dot is equal to f of x, where f of x is a nonlinear system, what we do is we are going to linearize the system about the equilibrium point, okay, or in the neighborhood of the equilibrium point, because we are going to discuss about the stability. We usually discuss the stability about the equilibrium point. The system may have one or two or multiple equilibrium points, and we are going to in what in the indirect method, what is done is the system equations are linearized about all the equilibrium points. For example, I have three equilibrium points, xe1, xe2, and xe3. If I am having three equilibrium points, and then the system is linearized about all the equilibrium points, and then we discuss the stability about the linearized set of equations. Okay, so if we have a linear set of equation, we convert it to a linear equation. We can represent x dot in terms of a into x. Once we have the A matrix, it is quite easy to devise to check the stability of the system. We have to just go and look into the eigenvalues of the system. Okay, so that is the method that we are going to discuss in the Lyapunov indirect method. Though it is a simple method, we are just discussing it for completion. Okay. And in the case of direct method, what we do is the exact the nonlinear equations are directly taken into consideration. But in this case, we have to define a function, a Lyapunov function here. We have to define a Lyapunov function, which in fact is quite difficult to find in most of the cases. And in that case, once we get a Lyapunov function to analyze the stability of the system, then this in fact is a very powerful method. Okay, so whenever we are not able to find out a Lyapunov function for a system, then we have to go with the Lyapunov. The other method that we usually do is the Lyapunov indirect method, and then we check the stability about the neighborhood of the equilibrium points. Okay, check the stability of the linearized system about the neighborhood of the equilibrium point. So now we will see how it is being done. Okay, it's the procedure is quite simple. Only thing, we have to linearize this set of equations, okay, about each equilibrium point. So now let us go to the discussion of how to linearize a set of equations. We are having a nonlinear set of equation. X dot is equal to f of x. So let us consider a small system, x1 second order system. X1 dot is equal to f1 of x1 comma x2, and x2 dot is equal to f2 of x1 comma x2. Okay, this is in fact generally represented as f of x, where f of x is, so if I write f of x is nothing but a vector which has f1 of f1 and f2 terms, which is a function of x1 and x2. Okay, x1 and x2. That's it. Okay, now the idea is to usually suppose we have an equilibrium. Suppose we have a point, the equilibrium point. It is the system, in fact, behaves like a linear system very near to the equilibrium point. That is why we are going to consider the system stability near the equilibrium point. And the next point is at the equilibrium. How do we find out the equilibrium point? We substitute the RHS of this equation to 0. Okay, and then we find out the equilibrium point. So at the equilibrium point, we can say that f of x equal to 0. Okay, so this we know. And what we are going to do is, in order to linearize the system, we are going to cause a very small perturbation in the neighborhood of the equilibrium point, that is xc, in both directions, delta x as well as delta x1 as well as delta x2. Okay, so in general we can write it as a vector delta of x1, delta of x near the equilibrium point. Okay, so once we have once we do the perturbation, we will see what happens to this equation. So x dot is equal to xc dot plus delta x dot. Okay, that is the change in delta. Okay, then what will be f of x? F of x is equal to xc plus f of xc plus delta x. So we can use a Taylor series of expansion here. So this becomes f of xc plus dou f by dou x at the equilibrium point into delta x plus the higher order terms. So since we are going to use the linearized system of equations, we are going to neglect the higher order terms here. Okay, so we are assuming that this is equal to 0. And we also know that this part definitely is equal to 0, right? This part is equal to 0 because we have this f of x equal to 0. This part is equal to 0. So this part is also good. So we have ended up with this term alone. So now we go and look at this equation. So if you see that at the equilibrium point, we have dou f by dou x at the equilibrium point. We make it as the A matrix. Okay, we consider it as a matrix into delta of x. So thus we have come up with a linearized equation which is of the form some x hat dot is equal to some A matrix into x hat. So once we have this set of equations, our problem has become very simple. Only what we have to do, we need to only analyze the stability of the system by looking at the eigenvalues of the A matrix for a particular equilibrium point. So we can do this at as many as equilibrium points as possible, and then speak about the stability of the equilibrium in the neighborhood of that equilibrium point. Okay, so we all know that dou f by dou x is nothing but a Jacobian matrix. We know how to write down the Jacobian matrix. Dou f by dou x is f is nothing but f is f1 of x1 comma x2 and f2 of x1 comma x2. Okay, this is x1 comma x2. This is f. So what would be dou f by dou x? Dou f by dou x would be the change in f1 along the direction of x1, along the direction of x1, change in f1 along the direction of x1, and change in f1 along the direction of x2. Similarly, here we have change in f2 along the direction x1, change in f2 along the direction of x2. So this is here, in fact, it is partial derivative because we are having terms x1 and x2. So this is in fact the Jacobian matrix. If we have n terms, it would be, the diagonals would be dou f1 by dou x1, x2, x3, etc. And the coming terms would be dou f1 by x2, dou f1 by dou x3, like that it would go on. Okay, so it's easy to form the Jacobian matrix. Okay, so this is in fact called as a Jacobian matrix, and we have to evaluate it at the equilibrium point to find out the A matrix. Okay, so we will look at a problem, and then we will get a more intuitive idea about like how the Lyapunov, from the how we can analyze the stability of the equilibrium point by using the Lyapunov indirect method. Okay, so we'll see this problem here, an example problem here. So I have considered a nonlinear equation here, x1 dot is equal to minus x1 minus x3 cubed. Okay, so what is the first process that we have to do? First, we have to find out the equilibrium points. Once we have the equilibrium points, then only we can speak about the stability of the system, about the equilibrium points. Okay, linearized system about the equilibrium point. So we once we put the right hand side of this equation to 0, we get 3 equilibrium points. This you have to work out and check whether this is correct or not. I am not very sure about it. So you check whether this is correct. I have got 3 equilibrium points here. Okay, so you have to check it. Okay, so first let us speak about the stability of the equilibrium point about the 0 point. Okay, we are going to bring in a small perturbation about the equilibrium point xe1. So what is the process? What is the equation? So we have delta x dot is equal to a into delta x, where a is the Jacobian matrix at the equilibrium point xe1. Okay, so first we will form the Jacobian matrix, which is common for all the three cases. So we have the Jacobian matrix like this: dou f1 by dou x1. What is this? Is f1 of x1 of t. This is f1 of x1 comma x2, and this is f2 of x1 comma x2. So what is dou f1 by dou x1? So this is minus 1. This term becomes 0. So it is minus 1. Dou f1 by dou x2 is 0 minus 3x2 squared. Okay. And dou f2 by dou x1 is minus 1, right? Minus 1. And dou f2 by dou x2 is minus 2. Okay. So I got this. So what is the value of this Jacobian at the equilibrium point xe1? We will get the A matrix for corresponding for the equilibrium point xe1. So what would be EA? Substituting x2 equal to 0, I get this matrix. Okay. So now once I have the A matrix, what I have to do? I need to only find out the eigenvalues of the system, right? That means which are in fact the poles of the system. So knowing the poles of the system, I can speak about the stability of the system about the in the very in the neighborhood of the equilibrium point 0, 0. Okay, so I got two eigenvalues minus 1 and minus 2, which are on the left of the imaginary axis. I can say that the equilibrium point xe1 is a stable focus. So we had classified it in one of the lectures. So we can say that xe1 is a stable focus. The system is asymptotically stable, right? The system is stable, in fact exponentially stable also. System is asymptotically and so exponentially stable for this case. Okay, so if we speak okay, so now we will look at the next equilibrium point and see see what happens to the A matrix. Okay, so we will go to the next equilibrium point xc2, and substituting the values of the equilibrium point here, we get this A matrix and we get the lambdas like this. Lambdas like this means the one of the lambda is on the right of the imaginary axis, the other one is on the left, right? So this shows that the equilibrium point xc2 is a saddle point. xc2 is a saddle point. Or we also know that one, as I have one of the eigenvalues on the right of the imaginary axis, the system is unstable near the equilibrium point xc2. Okay, so that means near, very near to the equilibrium point xc2, the system is unstable. And now we will go to the equilibrium point xc2, right? xc2. xc2 actually xc3, actually this is xc3. So I made a mistake here. So this is in fact xc3. One second, xc3. Okay, xc3. About the equilibrium point, we got something like this. So the lambdas for this case are complex, but on the left of the imaginary axis. So we have a stable node here. So we can say that xc3 is in fact a stable system. Yes, in fact, this is also going to 0 as t tends to infinity. So this is in fact asymptotically stable system. Okay, so what can we conclude from all these three evaluations about the equilibrium point? What can we conclude about the indirect method? So we can say that if we can consider this equilibrium point. Okay, if this equilibrium point, in this case this equilibrium point is unstable. Okay, since this equilibrium point is unstable, we can say that the linearized system is unstable about the equilibrium point xc2. Then we can say that the nonlinear system is also unstable in the neighborhood of the equilibrium point xc2. Okay, now if you go to the equilibrium point xc3, we can see that the equilibrium point is stable near equilibrium point. The linearized system is stable at the equilibrium point xc3. Okay, then we can say that the nonlinear system is also stable near the neighborhood of xc3. That means very near to xc3, the nonlinear system is stable. So this is the conclusion for the stability, and how this is the conclusion of the indirect method stability. Okay, so this is how we analyze the stability here, and these are the conclusions here. If the linearized system is stable, then the nonlinear system is stable in the neighborhood of the equilibrium point. If the linearized system is unstable, then the nonlinear system is also unstable in the neighborhood of the equilibrium point. Okay, and the last point is quite very important. Suppose I have some equilibrium point on the imaginary axis. Sorry, I get the eigenvalues or poles on the imaginary axis. Okay, can we conclude? The question is, can we conclude anything about the stability of the equilibrium point? Actually, no. The system may or may not be stable. Okay. So here we say that the system, for the linearized system, we can say that, okay, the system is marginally stable, but the nonlinear system may not be stable. Okay. May not be stable or can be stable. So depending upon some parameters of the nonlinear parameters of the system. Okay, so we cannot actually conclude much about the system of the linearized system if we get eigenvalues on the imaginary axis. Okay, but this indirect method is used when we are not able to find out a Lyapunov function using the direct method. When we go for the direct method and if we try to find out a Lyapunov function and we fail in that, we usually go for the indirect method for computation of the stability of the system. Okay. Now there is a problem based on to find out the stability of the system using the indirect method. This is the problem that has been given here, and you have to compute the equilibrium point of the system, and also um, equilibrium point of the system, and also the equilibrium and also stability of the indirect method, stability of the system by using indirect methods and by linearizing the system about the equilibrium points. Okay, so this is about today's session. So we can also think about in the coming lectures we will see about the direct methods of stability analysis. Okay, thank you.